Transistors are fundamental electronic devices that play a crucial role in modern electronics. They are used to amplify and switch electronic signals in various applications, including computers, smartphones, televisions, and countless other electronic devices. Transistors are the building blocks of integrated circuits, ICs, and are responsible for the digital revolution and the miniaturization of electronic components. There are two main types of transistors: bipolar junction transistors, BJTs, and field effect transistors, FETs. Here's a brief overview of each type. Bipolar junction transistors, BJTs are semiconductor devices with three layers of material: the emitter, base, and collector. They come in two main types: NPN, negative-positive, and PNP, positive-negative. BJTs can be used as amplifiers, switching devices, and signal modulators. They are characterized by their current-controlled operation, meaning the current flowing between the emitter and collector terminals is controlled by the current flowing into the base terminal. Field effect transistors, FETs are semiconductor devices with three terminals: the source, gate, and drain. They come in several varieties, including metal oxide semiconductor FETs, MOSFETs, and junction FETs, JFETs. FETs are voltage-controlled devices, meaning the current between the source and drain terminals is controlled by the voltage applied to the gate terminal. MOSFETs are widely used in digital circuits, while JFETs are more commonly used in analog circuits. Transistors are used in a wide range of applications, including digital logic, amplification, switching, voltage regulation, and signal modulation. In digital circuits, transistors are used to create logic gates, memory cells, and other building blocks of digital systems. Transistors can amplify weak electronic signals, making them stronger for various applications, such as audio amplification in speakers and radio receivers. Transistors can be used as switches to control the flow of current in electronic circuits. This is essential in digital electronics, where binary signals, 0 and 1, are used for processing information. Transistors are used in voltage regulators to maintain a stable voltage output, which is crucial in power supply circuits. Transistors are used in signal modulation for radio communication, enabling the transmission of information over long distances. Transistors have evolved over the years, becoming smaller, more efficient, and capable of handling higher frequencies. This continuous improvement has driven advancements in technology and has allowed for the development of powerful and compact electronic devices. Bipolar junction transistors, BJTs, are a type of semiconductor device that plays a crucial role in electronic circuits, particularly in amplification and switching applications. BJTs have three layers of semiconductor material and three terminals: the emitter, base, and collector. They are commonly categorized into two main types, NPN and PNP transistors. Here's an overview of how BJTs work and their key characteristics. In an NPN transistor, the central layer, base, is P-type semiconductor material, while the outer layers, emitter and collector, are N-type semiconductor material. In a PNP transistor, the central layer, base, is N-type semiconductor material, while the outer layers, emitter and collector, are P-type semiconductor material. BJTs operate based on the movement of charge carriers, electrons and holes, within the transistor structure. In an NPN transistor, electrons flow from the emitter to the collector, and this flow is controlled by the current entering the base terminal. A small current flowing into the base terminal, IB, controls a much larger current flowing from the collector to the emitter, IC. In a PNP transistor, holes flow from the emitter to the collector, and again, this flow is controlled by the current entering the base terminal. A small base current, IB, controls a larger collector to emitter current, IC. BJTs are often used as amplifiers. When a small input current, IB, is applied to the base emitter junction, it controls a larger current, IC, flowing through the collector-emitter junction. This current amplification is a fundamental property of BJTs and is crucial in applications such as audio amplification and signal processing. BJTs can operate in three main modes: active mode, cutoff mode, and saturation mode. In active mode, the transistor is on, and a significant collector current flows. It is used for amplification. In cut-off mode, the transistor is off, and there is minimal or no collector current. In saturation mode, the transistor is fully on, and the collector current is at its maximum. BJTs are used in various electronic circuits, including audio amplifiers, radio frequency, RF, amplifiers, switching circuits, and voltage regulation circuits. They are also used in digital logic gates, but their role has been largely supplanted by field effect transistors, FETs, in this application. Proper biasing, which involves setting the appropriate voltages and currents at the transistor's terminals, is essential to ensure the transistor operates in its desired region and provides the required amplification or switching function. BJTs have been instrumental in the development of electronic technology and continue to be used in various applications where their specific characteristics are advantageous. However, in many digital applications, MOSFETs, metal oxide semiconductor field effect transistors, have largely replaced BJTs due to their lower power consumption and higher switching speeds. Field effect transistors, FETs, are a family of semiconductor devices that play a critical role in modern electronics, particularly in digital and analog circuits. FETs are characterized by their ability to control the flow of current between two terminals, the source and drain, using an electric field applied to a third terminal called the gate. There are several types of FETs, with the metal oxide semiconductor field effect transistor, MOSFET, being the most common and widely used. MOSFETs have three terminals, the source, gate, and drain. They are typically made of silicon and use an insulating oxide layer, usually silicon dioxide, between the gate and the channel region. MOSFETs come in two main varieties, N-channel and P-channel, depending on the type of charge carriers, electrons or holes, they use for conduction. SHVETs also have three terminals, the source, gate, and drain. Unlike MOSFETs, SHVETs are made of a single semiconductor material, either N-type or P-type, and their operation depends on the reverse-biased PN junction formed between the gate and the channel region. MOSFETs operate by applying a voltage to the gate terminal, which creates an electric field in the oxide layer. This field either enhances or depletes the flow of charge carriers, electrons for N-channel, holes for P-channel, in the channel region between the source and drain terminals, depending on the type of MOSFET. SHVETs operate by varying the width of the conducting channel in the semiconductor material. A voltage applied to the gate controls the width of the channel, which in turn controls the flow of charge carriers between the source and drain. One of the key advantages of FETs is that they are voltage-controlled devices. The gate voltage determines whether the FET is on or off and the level of current flow between the source and drain. This makes FETs very suitable for digital logic applications. FETs have very high input impedance, which means they require minimal input current to control the flow of current between the source and drain. This makes them suitable for high-impedance signal processing applications. MOSFETs are widely used in digital integrated circuits, ICs, as switches and amplifiers. They are the primary component in modern microprocessors and memory devices. SHVETs are used in various analog applications, such as amplifiers and low-noise signal processing circuits. FETs have high input impedance, which means they are minimally disruptive to the circuits they are connected to, making them suitable for applications where the input signal must not be loaded down. In summary, field effect transistors, particularly MOSFETs, are essential components in modern electronics. They are integral to digital integrated circuits, power amplifiers, analog signal processing, and many other applications due to their voltage-controlled behavior and high input impedance.